Hi, my name is Tom Groenveld. I'll be presenting some of the research I carried out at the Gurion University in Israel about numerical modeling to optimize nitrogen fertigation and considering the transient drought and nitrogen stresses. The data I modeled was from cucumber plants, which you see here on the picture over here. This was one of the most meaningful papers that I wrote. It was just recently published in Agricultural Water Management because the data was actually modeled, and it's very nice to measure data. It's a lot of fun and very interesting, but when you take the data and put it in a model, it becomes available for others to compare and to build on. And that's something that Hari Vereken here has done a lot of, and this session is dedicated to him. Hari Vereken up here. Long live Hari. I'm not going to say a lot about him, but I do want to point out that he has this publication here dealing with simulation of water nitrogen behavior, so a topic that's close to my heart, and he's been dealing with this since I was in kindergarten. In nitrogen fertilizing or fertigation, we try to stay in this optimum range here, where an increased application of nitrogen doesn't result in an increase in yield anymore. But because a reduction in yield is very great if we don't apply enough nitrogen, so most farmers try to stay in this range where they're more safe. But this range causes a lot of pollution, with nitrates leaching to the groundwater and nitrous oxide emissions. With irrigation, farmers also try to stay close to what the plant demand is, which depends on the climate and on the plant size. And when you fertigate or apply fertilizer, that ideally is also linked to the plant size, which determines the nitrogen potential uptake of that plant. These processes affect each other because if the plant size affects also the transpiration and also the nitrogen uptake. And so these complex processes, we can use numerical models to simulate what happens with them in the soil and to try to optimize plant nitrogen fertigation. Our objectives were, these factors are also affected by, of course, by root distribution, by the growth stage, by the soil type, and the water quality. So these all should be considered in the simulation models that we use. Our objectives were to calibrate and validate the combined active, passive, and compensated nitrate uptake functions in Hydrus 2D, 3D, and to optimize nitrogen fertigation by maximizing yield and minimizing loss by means of this optimized by means of this calibrated model. So here you see how a simulated plant could look like in Hydrus. The root zone density distribution is distributed according to a function, and then the plant transpirative demand is divided over the entire root zone according to that density distribution. The nitrogen uptake is also considered according to that same density distribution. First, the uptake is considered passively. We're limited by a maximum concentration, and the rest that's not taken up passively is considered to be taken up by active uptake means. And that potential active uptake, so the total uptake minus the passive, is distributed also across the root zone according to the same distribution here. So that looks like this. Then you get the active potential uptake at each node in the root zone. The active uptake is then considered according to Michaelis-Menten kinetics. And we also consider compensation of nutrient uptake. That's just a factor that you can add in here so that roots can compensate for lack of uptake from other zones where they can take it up more easily. For our methods, we had to modify the Hydrus model as the current version can't consider nitrogen transformations and active nitrogen uptake at the same time. So that was implemented, and then we added a function that reduces the potential transpiration due to nitrogen stress. There is such a function that looks very much like that, which reduces the potential nitrogen uptake according to transpiration stress. It hasn't been validated yet, but that already exists in the model. And so we used an experimental data set to calibrate and validate, which was cucumbers, I mentioned that already, growing in perlite with 3 nitrate concentrations and 6 irrigation rates, which were irrigation over transpiration. The irrigation over transpiration rates are here on the x-axis. The 3 colors are the 3 different nitrate concentrations. And so with each different irrigation rate, according to as a function of transpiration, the amount of nitrogen fertigated to the plots increased. So we got 18 different treatments here. When we take the fertigation rate and put it on the x-axis and see how much went into the plant and how much went into the drainage, we see that there was a saturation here, or getting close to saturation, and this was increasing exponentially. The plots that we grew in looked like this. They were styrofoam boxes filled with perlite. And the cucumber plant, there were 3 cucumber plants in each box. The drainage was collected, so it was a lysimeter system. And we modeled half of this root zone with a line of symmetry, and the domain looked like this. At the top here, there's a time variable flux boundary condition. At the bottom, there's a seepage phase boundary condition. And the root zone distribution looked like this. After 2 weeks, in the first 2 weeks, it was growing, and after that, it stayed fixed for the whole season. So the calibration results look like this. The nitrogen fertigation, of course, we knew that because we measured it. And the drainage, we also measured over time. And the line is the simulated measurement, or the simulation, which was very close to the measured. And the green is the uptake. We only knew the total uptake at the end of the season. So this is the simulation over time. And the red line is the emissions. It's considered a first order decay reaction. And the water flux looked like this. We measured the irrigation, drainage, and transpiration over time, and so that was very close. The simulated was very close to the measured data. Just to remind you, the treatment that we used for optimization is this highest one here, which received the maximum amount of fertigation. Then we did a validation, so we put all 18 treatments into the model, ran the simulations, and then we saw that the model explained very well the reduction in transpiration with reducing nitrogen applications. You see here these color codes are from the graph that I showed you before, with the 3 different treatments. In the lighter colors are the lower irrigation rates, and the nitrogen uptake same, and the nitrogen leached also lined up very well. The nitrogen emissions were less good of a correlation because, of course, there's a more complex things happening there than a first order decay reaction. An interesting thing that we noticed in the results was that the percentage of nitrogen that was taken up actively by the plant was different than what would be expected from a commonly used equation, which is Barber's equation. According to Barber's equation, the amount of active uptake is the total uptake minus the passive uptake divided by the total uptake. And so if we calculated that for the simulations, then we saw here that at the high fertigation range, it would underestimate the active uptake, and the active uptake it estimated would decrease with reduction in fertigation, so in a deficit zone. Whereas in the Hydrus model, the prediction was that the active uptake would increase with reduced nitrogen fertigation. This is due, we believe, to the fact that in the Hydrus model we have a spatio-temporal consideration of the nitrogen distribution in the root zone, which isn't included in this formula. This is used as a single concentration for the root zone, which of course is not accurate. When we optimize, we ran simulations to find the optimal concentration and nitrogen application ratio, and then we came to a level of, we found that 40 milligram application per square meter was the optimal application range for this under the conditions that we grew in. And you see here that there's the highest uptake and there's the highest transpiration, while the nitrogen emissions here were lower than the higher concentration of nitrogen application. And here we're a bit higher than this, the leaching was a bit higher than this 105 milligram per liter concentration. But in total, the amount of nitrogen lost by leaching and emissions was the lowest for the 75 milligram per liter concentration, whereas the transpiration and the uptake was the maximal. The water use efficiency is shown over here. And so finally, to conclude, the optimal nitrogen concentration for fertigation of cucumbers grown in perlite under the conditions described in this experiment was 75 milligrams per liter. And the modeled nitrogen stress function explained 82% of the reduction in transpiration that we saw. And finally, the percentage of active uptake increased substantially under conditions of nitrogen stress. And so I'd like to acknowledge the research station where I carried out the experiment that was used for the experimental data to calibrate and to validate the model, and the Gurion University where I carried out the research, and the funding agencies here. If you have any questions, I'd be happy to answer them by the chat line or by email. Thank you very much.